So we're going to have one more thing to worry about, and that is friction. And so what I'm going to do in terms of some notes is work out some example problems that are similar to what your homework will be so that you can see where the friction comes in. And basically then that'll lead to our F-nets, and then that'll lead to things like acceleration and our equations of motion. So in this first one, and this is on your Google Classroom, we've got a 12,000 Newton car. It's going 75 miles per hour. The coefficient of friction is 0.15. Now, I'm not going to worry about sliding friction versus static friction. You did a little bit of reading. Hopefully you encountered that. We're always going to be in motion for these things. We're not really going to worry about the cases in which we want to get things started per se. It takes a little bit more force to overcome the static friction than it does once it's in motion. So I won't necessarily specify, but there are two types of coefficient of frictions. One of them, again, refers to getting something started. And then the other one refers to it's already in motion. So here we have a car that's already going 75 miles per hour. And there is friction between the tires and the road. And so if I basically take my foot off the gas pedal and allow the car to coast, if you will, it will eventually come to a stop. And the question is, how far and how long does it take to come to that stop? And the first thing you need to recognize is, hey, I need a drawing. So let's make our drawing first. And, I've let my foot off the gas pedal. So there is no FA. There is only, along the line of motion, a force of friction. Now, perpendicular to that, since I'm on level ground, it still has weight. And there still is a normal force. But these are the only forces that are going to be applicable because, again, I'm not pushing on the gas pedal. Now, the force of friction equals the coefficient of friction times the normal force. So the force of friction is always related to the normal force. And in this case, that means, of course, to its weight. Now, what about Fw? Well, Fw, that's just mg. And let's see, in this particular case, what am I told? I'm told that I have a 12,000 Newton car. Okay, well, that 12,000 newtons, oops, one more zero. That is the Fw. Okay, it's going 75 miles per hour. There's my coefficient of friction. In this case, because I'm on level ground, the force of friction is going to equal mu, the coefficient of friction, times Fw. So the 0.15, it does not have units, times the 12,000 newtons. So The force of friction is 1800 newtons. And it is the only force that's slowing the car down. Now, eventually I want to figure out how far and how long does this take. So I need acceleration. And to get acceleration, since that's the only force that's involved, I have to divide by the mass. Now, I don't actually have the mass at this point. However, if I take the weight and divide by gravity, then I have the mass. And this comes out to be basically 1,200. Thank you. This comes out to be 1,224.5 kilograms. So, my acceleration then will be 1.47 meters per second squared. Now, the question is about coming to a stop. So my VF is 0. My VI was 75 miles per hour, which if I go through, let's see, what we had before, let's see, what do we say, 26.8. That'll be 33.5 meters per second. So now I have A, I have VF, I have VI. I can go ahead and solve for how long it's going to take before it comes to a stop and how far it's going to move. If I use my first equation of motion, I can get the delta t. Now, at this point, you might be thinking, well, wait a minute. My VI is positive. What about my acceleration? Please note, I did not get it through the math, but from directions, the car is moving this way. Force is in the opposite direction. The force is slowing me down. So in fact, that is a deceleration to bring me to a stop. So it gets a negative. It wasn't from anything I did up here. It's from my picture. It's from my direction. And so I have to consider, and therefore my negative signs will cancel out. It's a negative 1.47. Otherwise, you might be concerned and go, well, wait a minute, I'm going to have a negative time. I can't have negative time. And basically, it's going to take about 22.8 seconds. And the easiest one to do is the third equation of motion to find out how far. And so in this case, That's how far it'll move. And so that was the first problem. And even though it's a relatively simple problem in terms of we're not on a hill or anything, some things to note is, every problem is not necessarily going to tell you the mass. I had to get that from the FW. Once I found my net force, and again, I didn't put net force up here at all because there was only one force. So there's no really reason to say an F net force, but that's the only force. So by default, it's also my F net. So that again, that is problem one. Any questions? All right, next we have a box is pushed across a horizontal floor at a constant speed of 8 meters per second with a force of 24.5 newtons. What is mu? So, again, start off with the picture. Now, this box is being pushed. So if you want, there's my FA. I'm pushing it. And there is friction. And friction is always opposite the direction of movement. So if I'm in my picture here moving to the right, my friction has to be to the left. Now, my F net is going to be that. But that has to equal 0. Why? I said I'm moving at constant velocity. If I'm moving at constant velocity, then I'm not accelerating. Therefore, the frictional force must equal the applied force, which was stated to be 24.5 newtons. Now, technically speaking, I left out some forces in my picture. I left out the vertical forces. And I need that because, of course, now in this problem, it's a 5 kilogram box. And let's see that. 49 newtons for my FW. But we've already found out from our FNet that has to be 24.5. So how do I get mu? And again, mu does not have any units. Any questions on this one? Now, part B here says redo part A, but now the box is accelerating at 0.8 meters per second squared. Okay, so what does that change? Well, our FNet is still that, okay? But now there is an acceleration. It's accelerating at 0.8 meters per second squared. In other words, it's not going to stay at 8 meters per second. It's not going to stay at a constant velocity. Well, now that's how I get my FF. And of course, the rest of the problem isn't going to change from what I had before. It's the same 5 kilogram box. So it's got the same weight. But now the mu is a little bit less because, in fact, it is accelerating a little bit. It's given to you in the problem. Part B, redo part A, but now the box is accelerating. So yes, you were given that. No problem. So literally, one of the things to note about friction problems is I'm always going to go back to FNet. If there's an applied force and a frictional force that's going to oppose it, then I have to take that into account. And then the question becomes, am I moving at constant velocity, in which case FNet is 0? Or am I accelerating or decelerating, in which case FNet is MA? And so that changes a little bit how to find my FF. All right, next. And I know it's kind of small text, but you have it also on your Google Classroom. I have a 240 Newton lawnmower, that's its weight, whose handle makes a 50-degree angle with the ground, and it's going to be pushed with a force of 120 newtons. If the lawnmower moves at a constant speed, what's the coefficient of friction? So what's different about this problem from what I did before is here my FA, my applied force, my pushing, was in line with the direction of motion. Now I'm going to have a force that's applied at an angle, which means I need my components. So let's go ahead and make a picture of this one. So my applied force, now that it's at an angle, as I said, switch it into components, and I'm just calling one of them the vertical component and one of them the horizontal component. Here's my 50 degrees. So first off, let's go ahead and find our components. So the vertical component will be the applied force times the sine of the angle. So let's see, it was 120 newtons times the sine of 50. The horizontal component goes with cosine. But this is a friction problem. So anybody who's ever pushed a lawnmower knows that depending on how high the grass is, it'll work against you. And let's see, let's go ahead and make sure that we also consider these things. Now, in terms of our motion, I have to use the horizontal component, not FA. And the problem said, hey, we're moving at constant speed. So that has to be 0, which means, of course, that the frictional force has to equal that horizontal force. And again, we've got this. But if we think in terms of our net forces in the y direction, because I am doing things at an angle, I've got a component of that applied force that's pushing down. So really, I have to think about it. Oops. Like that, considering the directions. And of course, this is 0 because it's not sinking into the ground and it's not moving up into the air. So my Fn is actually a little bit different than in that horizontal world I was in the last problem. And it is assumed that when we talk about pushing at an angle, we are pushing down in addition to pushing forward. So my lawnmower, my SV, and we already said in the problem, its weight was 240. So that's actually the Fnet. This is a big difference from something that we've done before. Fn is not just equal to Fw. We're also pushing down. And so the Fn has to equal both of those forces because, again, it's not sinking into the ground and it's not lifting up into the air. So now I can do my mu. The FF is 77.1. The Fn, the 331.9. So there is our coefficient of friction. Now, part B said redo part A, but pull the lawnmower instead of pushing it. Okay, so I'm going to redraw my picture real quick. I could just use the picture up there, but let me redraw it so that we can see where all the forces are. So before I worry about solving it, just take a look at the pictures for a moment and see what's changed. Since I'm pulling my lawnmower instead of pushing it, now my FH is this way. FF has to be the opposite direction. It's always opposite motion. So I am saying I'm basically pulling left. Here I was pushing right. Now I could have said pulling left, or pulling to the right, but just to make the pictures line up exactly, I've made it done that way. So my F net is still going to be just like it was before. And since the only thing that I'm changing is that I'm pulling instead of pushing, still at constant speed, so my FF is still going to be equal to the FH. I didn't change the applied force, so that's still going to be the same 77.1 newtons. So the horizontal portion of the world doesn't change at all. Pushing, pulling, the friction is still in the opposite to whichever way I'm trying to move. However, note how my F net in the Y direction has changed. Because I'm pulling instead of pushing, FV is now up instead of down. And of course, FW is still down. It's always down. And that's still going to be 0. So now my Fn, my normal force, is going to be the difference of the weight. And by the way, you probably experienced this without really paying attention to it. It is often much easier to pull something than to push it once you've gotten going, because in fact you're lifting it a little bit, and so you are effectively reducing the normal force a little bit. And since friction is related to the normal force, you are reducing the effective amount of friction in the process. So in the pushing world, the normal force is the vertical component plus the weight. In the pulling world, the normal force is the weight subtract the vertical component. Now, the forces didn't change. The same two forces that we had up above in part A. So it's still going to be our 240 newtons, but now it's subtracting the 91.9 newtons. Which gives me that. The mu is still FF over Fn. And there is our new mu. Now, in an ideal kind of thinking about things, the mu is related to the contact between the two objects. So between the lawnmower and the ground, the grass. The mu should not have changed between these two. So what does that mean? Really, when we get right down to it, is in the pulling, I would not have needed as much force to maintain that constant speed that I did in pushing. So if we assumed for a moment that it was still the 0.23, then the FF would now be that. And again, this is assuming the 0.23. And what we can then do is remember that also since we're at constant speed, FH had to equal FF, and therefore FF is FA cosine, or in other words, I can find out what FA is. And so that 34.1 divided by the cosine of 50 turns out I would only need 53 newtons for my applied force instead of, what was it, the 120 that I did when I was pushing. I actually would only need 43 newtons of force pulling instead of the 120 pushing to maintain the same speed, that constant speed. Assuming the coefficient of friction was the same, because that's really dependent on the contact between the two surfaces. It's not really dependent about how much I'm pushing or pulling. So the mu I calculated was different because I made some assumptions, but in reality, the real assumption should have been the mu doesn't change. What would have changed is how much force I needed to apply to maintain a constant speed. If I really was pushing or pulling with the same force and the same mu, I would end up accelerating, not staying at constant velocity. All right, and then we got a part C. It says redo part A, but now the ground, now we're on a hill. So, new picture. This will be our last part. And obviously this is not 2 degrees. I'm overemphasizing just to make things stand out. But I want you to see where all the different forces are. And I'm still at constant speed for this one. So I'm still going to have my components. And I'm going to assume pushing because I'm redoing part A. But now that I'm on a hill, and granted, it's not a very big hill, but there is going to be a component of the weight of the lawnmower that I'm going to have to push against. FP is always downhill. And note that my FN is now opposite the component of the weight, because it's always perpendicular to the surface I'm on. All right, so we got lots of components here. So let's go ahead and just do that part first. So my FE is still going to be FA sine, and this is still the 50 degrees because we're still doing the same part A. And we were at 120 newtons of force, sine of 50. And so let's see, we already did that once. That was our 91.9. Our FH cosine and so that's still the 77.1. But now we got to worry about FP, which is FW sine. And let's see, we had a 240 Newton. And let's see, sine of 2 degrees. So not much to it, but there's a little bit of FP. The perpendicular component gets cosine. And this is pretty close to what it was before. Almost the whole 240. So there's not very much that's separated. So I can do all those. Now, first off, our orientation has changed. We always do our orientation based on how our moving is going. So since we're going up the hill, we have to do X that way and Y perpendicular to it. So the F net in the X direction, well, what do we got going? Well, we've got our FH pushing up the hill. We've got our FF working against us. And we've got that component of the weight that's down the hill. And of course, the higher the hill, the greater that component would be. So this is what's different now from what I did in the previous part B. I have this to worry about. And again, that's going to equal 0 because I'm moving at constant speed. So now my frictional force is the horizontal component, subtract the parallel component. Okay, we already had that. That's the 77.1. P, that's the 8.4. So there's my FF. And again, remember, where are we trying to get to? We want to find mu. That's where we're trying to get to. Well, now we got the FF part. I need to think in terms of the vertical. Well, what's going on in the vertical? Now, well, I have my Fn going up. My Fv is going down. And not Fw this time because I'm on a hill. I have to do the perpendicular component of the weight going down. And of course, it's not sinking into the ground and it's not rising into the air, so that has to be 0 as well. Or another way of putting it, not moving perpendicular to ground. So my Fn then has to be those two guys. Well, the FV, we have the 91.9. And this one is 239.8. So there's my Fn. The FF. The Fn. Now, note, if I go back to part A for a second, that the denominator part was very close, 331.9 versus 331.7. The top part changed just a little bit. Instead of 77, it became 68 because we had to consider the FP. And so, my mu, a little bit less than it was in part A. But really, what I want to hone in on is how that picture is changing as I bring in more things to consider. And I'm always coming back to my F-net equations. And with friction, I have to worry about not only the x direction in line with my movement, but I also have to worry about the y direction. Something I didn't have to worry about at all when I wasn't considering friction. So that's it for your notes.